To make something up.
Not you.
I know. Okay, well, the last of us are collecting our snacks. I don't know if you guys saw that Mark got these delightful little eggs this time, which I think are going to be delicious. Thanks for coming. Today we're talking about the connection between galaxies and their dark matter halos, which is one of the most pressing topics in galaxy formation currently. And we have, again, an observer and a theorist to discuss this with us. We'll start off with Sownak Bose. Oh, you changed it. Okay, well, his name doesn't actually have a Z in it. Sownak Bose is an ITC fellow by day and an aspiring sports writer by night. I'm not sure if you knew that, but back to it. And he'll be talking about different models for dark matter and dark energy in illustrious, mostly.
Actually, maybe just one slide.
Okay, sorry. Oh, he'll talk about what he talked about. Jabran Zahid is a Clay Fellow here. He mostly studies the chemical evolution of galaxies, but has recently become interested in connecting galaxies and their dark matter halos. And I kind of want to just, yeah, I shouldn't make up your hobby. Okay, take it away, Sam.
Okay, cool. So what I wanted to do today was provide will end up being a rather incomplete census on some of the theoretical aspects to do with the galaxy halo connection. And I guess a good place to start is to start with the start. So, you know, in our sort of picture for structure formation of galaxy formation, everything sort of starts with a couple of question marks, really. So we think that there's some sort of fluctuations in the sort of primordial quantum field, and these fluctuations themselves are sort of amplified further by some sort of violent expansion process, so which, you know, for which inflation might be one possible hypothesis. So inflation then expands and amplifies these fluctuations to the level of 1 part in about 10 to the 6 in terms of density fluctions, which are observed as the temperature fluctuations in the cosmic microwave background, which missions like Planck and WMAP have sort of detected so beautifully. And then it's from here onwards that actually we have a little more handle of what's actually going on. And essentially the translation of these primordial fluctuations in density into the swathe of structures that we see around us in the cosmic web in terms of filaments, dark matter halos, and walls is something that is sort of allowed by the process of gravitational instability. And it's something that we've really sort of managed to pin down quite well with the development of semi-numerical and numerical techniques, specifically cosmological simulations. And the idea is really to then connect this image with the image from galaxy redshift surveys to actually try and understand how the visible galaxies themselves are sort of embedded within the structure. So really the industry of the galaxy halo connection has a very simple sort of philosophy to it, which is how do you bridge the gap between the cosmic web that we can simulate and the galaxies that we observe. And the complexity lies in the fact that one particular part of the process is, we think, well understood, whereas the other part, which is actually visible and observable, is less well understood. And the hope is that in the process of doing this, we'll understand a couple of different things. So firstly, we can hopefully understand how galaxies are formed and what are the important processes required for galaxy formation. Then with the generation, or with an understanding of how galaxies actually populate dark matter halos, we can come up with simple techniques to actually put galaxies into very, very large simulations many, many times over, generate more galaxy catalogs, and then compute things like covariance matrices, which can eventually help pin down things like cosmological parameters, which will be measured very precisely by future galaxy surveys. And finally, we want to understand how to map the actual distribution of dark matter and possibly learn something about its nature and the nature of gravity on very large scales. Okay. So in its simplest manifestation, I think the galaxy halo connections philosophy can be boiled down into basically one very simple line, which is we want to find out a distribution function or a probability distribution which basically tells you how many galaxies you can fit into a dark matter halo using some particular property. So specifically, I guess, the mass of the halo seems like a fundamental property to start with. And then you can try and use some kind of methodology to figure out how likely it is that you will have a central galaxy, or how many satellite galaxies you expect to have in this halo, given its mass. And this particular formulation is often sort of titled under the name of the halo occupation distribution. You can then sort of add a second level of complexity and not just ask about the sensors of galaxies, but rather some integrated property to do with the galaxy itself, such as its stellar mass. So you could invert the equation to something like this. So what is the probability that you have a galaxy of a particular mass given some property of the dark matter halo? Okay. So there are a number of theoretical approaches that have come up in the last couple of decades, and so what I'll try to do in the next few minutes is to provide some summary of this, and the next slide is really borrowed from this recent review of the subject by Risa Wexler and Jeremy Tinker. So to begin with, we have the, I suppose, the well-known case of halo occupation distribution model. So this is a very simple ansatz which says that we are not going to care about the substructures of dark matter halos. We only care about the parent host halo, and we'll come up with some kind of framework which tells you, given the mass of the halo, what is the mean occupancy of central and satellite galaxies within this halo. Okay, so it's a very, very simple start. You can then go one step further and start considering not just halos, we can start considering their substructures as well, in a process called abundance matching, where what you do is you start rank ordering your galaxy catalog by stellar mass or by luminosity, and you rank order your halo catalog by some particular property, such as mass or circular velocity, and then you just say that the brightest object goes into the most massive halo or the deepest potential well. Okay, so you just match it very simply on the basis of that. So from subhalo abundance matching, then there is the enterprise of the empirical forward modeling, and this is really something that has been pioneered by the likes of Peter Beruzzi, Ben Moster, and even people like Sandro and Charlotte here who worked on this. And now we're actually starting to use not just the information about simulations at a particular snapshot in time, but we're actually using the merger histories of dark matter halos as well. These merger histories can be computed using semi-analytic techniques, or you can actually use the information that we compute out of simulations. They each have their flaws and pros, I suppose, but that's a separate particular subject. And the idea is that once you have these merger histories, you can parameterize the connection between the star formation rate of a galaxy and the merger history or the accretion history of the halo in some kind of parametric form, and then using a large census of data that you wish to replicate with your model, you can sort of constrain these parameters better. Then comes the oft-maligned semi-analytic model, and this is probably the one that has been around for the longest period of time, and semi-analytic models actually try to put some physical interpretation into what's actually going into the model. So there are some possibly simplistic, overly simplistic treatments of how gas would cool, how stars form, how feedback takes place in the form of supernovae or AGN, and so on and so forth, run through the merger histories of halos from cosmological simulations. And I say oft-maligned because they are usually blessed with a number of free parameters, which people sometimes take some exception to, but I think ultimately it's not really that much of a problem, because it just reflects that galaxy formation is not a very easy process. And finally, there are hybrid dynamical simulations, which have really sort of exploded in the last decade or decade and a half, where we're actually co-evolving baryons and dark matter and have their relative interaction and interface taking place through high-resolution simulations. So I took the liberty of taking these models and sort of placing them on this rather frivolous diagram of complexity of models versus what their actual motivation is. So if you're a particular fan of any particular manifestation of these models, don't be sort of affected by the relative placement of these points. It doesn't actually really mean much. But essentially, you can sort of break it up into models that are more physically motivated going towards the right-hand side, and the models that are more empirically motivated on the left-hand side. And the sort of points are sort of kind of colored in grayscale based on how long it would take to actually run each of these things on a particular project. And even though they're sort of separated disparately in this diagram, I wouldn't say that they actually are completely separate to one another in any means. And really what you would actually use for your galaxy halo connection model really depends on the scientific question that you're trying to answer. So for example, if you are interested in generating galaxy catalogs and mock catalogs for large-scale surveys many thousands of times over, then you would probably go for something simple and flexible. So an HOD or an abundance matching technique would be the way to go with that. Forward models and semi-analytic models are really good for exploratory purposes. So these models allow you the flexibility to turn on and turn off various physical processes to understand how a particular implementation is affecting stuff. They can be done pretty quickly at much less computational cost than what it would take to do in an equivalent hydrodynamical simulation. And finally, you have hydrodynamical simulations where you're actually trying to understand the physical effects of various processes and how the total matter distribution actually responds to the way in which patterns are modeled. And even apart from this, I would say that the sort of hierarchy over here is really kind of analogous in some ways to the way that the various components of the cosmic distance ladder sort of talk to one another. So what I mean by that is that they are essentially sort of informative to the sort of next subsequent process. So let's start with, say, the case of abundance matching or halo occupation models, for example, right? So what typically happens is you run a dark matter simulation and you construct a halo catalog, such as the one at the top there, so there's a halo mass function. Now the idea behind your abundance matching or your HOD framework will be to then translate this into some mock galaxy catalog, where you're trying to replicate some galaxy abundance, and perhaps another statistic like the clustering of galaxies. So clearly you have some framework for doing so, and in the HOD prescription, where you essentially have is a distribution function that tells you how satellite galaxies need to be placed in these halos and how central galaxies need to be placed in these halos, and there are some free parameters that you can adjust so as to actually replicate these data sets in your mock catalog. And so one of the things that you can then compute out of this is a diagram which looks like this, which is halo mass on the x-axis and the halo occupancy, or essentially the average number of galaxies within a halo of a particular mass on the y-axis. Okay, and you'll see that there are a number of different parameters here. So this is one particular parameterization of the HOD prescription, and there are these free parameters which are essentially fit so as to replicate the abundances and the clustering that I showed in that we're trying to target, essentially, right? And so what's shown here is the sort of mean occupational centrals and the dashed curves, and of satellites and the dotted curves, and the blue solid line is just the sum of the two. And so for the centrals, you can see that for this particular mock catalog, everything above 10 to the 12 has a central galaxy typically, but then this sort of rolls over, meaning that you get to a point where eventually only one in every so many halos actually end up having a galaxy in them. And essentially what these parameters do is give you some sort of physical interpretation as to how quickly or how slowly this relation turns over. Right? And the same can be done in terms of what it means for satellite occupations to actually dip below zero. So there's some minimum halo mass above which satellites are expected to form, and conversely not. I should say that this functional form is not arbitrary. This is the HOD's functional form is actually motivated by early generations of hydrodynamical simulations and semi-analytic models, where you can actually measure these things and come up with shapes that look something like this. So one very often computed quantity that comes out of these things almost for free is the so-called stellar to halo mass relation, or as it's plotted here, the stellar to halo mass ratio versus halo mass relation. This is taken from Peter Peruzzi's recent work. And this is the sort of familiar shape where you see that there's a sort of peak in the efficiency of galaxy formation, I suppose you can call it, at around the scale of galactic halos, happily enough. And then this relation sort of falls over on either end, saying that essentially that the efficiency of galaxy formation drops towards lower and higher masses. The different curves are basically showing you compilations of this particular relation obtained by other authors using slightly different techniques, abundance matching, conditional loss functions, and so on. And
this is for the central galaxy, the mass?
Well, yeah, I mean, it could be done for both, I suppose, but yeah. You could do it for centrals or satellites, really. But I think it makes more sense when you're talking about halo mass to do it for central galaxies.
Yeah, no, I meant if it's central galaxy or the entire mass in all galaxies.
So that's an interesting question. So especially at the high mass end, what you actually use as the stellar mass of the galaxy has an impact. So typically when people in, say, Illustris will talk about what is the central galaxy mass, they talk about the mass contained within some aperture, as opposed to the mass contained within, say, the entire friends group, or the mass enclosed within 100 kiloparsecs or whatever. So, but there is some stochasticity there, but the general shape, I think, is pretty.
Because from the previous plot you showed, it seems as at large masses, you just get lots of small satellite galaxies.
Yeah.
So it might
but the mass is dominated by this.
It's still dominated by.
Okay. So what else was I going to say? Okay, so the abundance matching itself tells you essentially what the shape of this relation is, but not necessarily what the physical interpretation is for why it's dropping on either end. So that's something that we can then, through hydrosims or through simulated modeling, try to put some physical interpretation for. So an important question to ask is, what are actually the appropriate variables when it comes to making the connection between galaxies and halos, right? So in the simplest case of abundance matching, you could just say that, okay, perhaps the most important thing is some way to characterize what is the depth of the potential well of the dark matter halo in which I want to put my galaxies. So this is some work that was done by Charlie back in 2006, and what this is showing is essentially the two-point clustering of galaxies in the Sloan digital sky survey shown in the points there as a function of separation. And the solid lines are predictions of cold dark matter simulations which have been augmented with an abundance matching model to replicate essentially the Sloan catalog. And you can see that the predictions of the clustering from the theory is sort of in excellent agreement with the actual observed value of the clustering. And almost surprisingly so, because essentially the abundance matching is a one-point statistic. You're fitting it to an abundance, but you're managing to fit the two-point statistics quite well. So what this is really telling you is that despite this very simplistic assumption that the heaviest things contain the brightest objects, there's at least at some level some evidence that the depth of the potential well is not a bad first guess. But what is particularly important is whether you decide it's halo mass or in fact something else that characterizes this best. So this was shown by the work by Reddick et al., where they again look at the clustering of galaxies, but now comparing with data and using abundance matching based on different ways to parameterize what the depth of the potential is. Whether you use halo mass at present day, whether you use a peak circular velocity, the peak Vmax, or the max Vmax over all history. And you see that on large scales, you get very good agreement in all cases, but the small scale clustering is quite manifestly different. And you can actually look into simulations to try and understand why this happens. So this is some results from Illustris, which is actually looking at how galaxies or satellite galaxies are distributed within host halos of some particular mass. The stars are showing how the luminous population is actually distributed, and each of these curves are showing how the dark matter halos in a dark matter only simulation are distributed. So if you just simply select by the present day mass of subhalos, which are prone to the effects of tidal stripping, you don't actually learn something about the original potential well within which the galaxy actually formed, which would have been the right way to do things around. But in fact, if you select by the peak circular velocity, or essentially some metric that takes into account the depth of the potential well prior to stripping actually taking place, then you actually get something that more closely resembles what is observed in the luminous population. Okay. So there's been a lot of focus recently on trying to extend the halo occupation and other galaxy halo connection models to higher order and going just beyond empty mass. And in the case of dark matter halos, you have properties like concentration, environment, formation, redshift, and so on, all of which is classified in the name of assembly bias. On the galaxy side of things, you can ask, do we only care about trying to figure out what the probability or the likelihood of stellar mass as a function of halo mass is, or do we care about more differential quantities like what the actual star formation rate is as a function of halo mass, or what the red and blue colors of galaxies is, what their stellar velocity dispersion is, their gas content, and so on? And I think at some level we will reach a roadblock, because I think from a model building perspective, it seems very unlikely to me that there will ever be any number of combination of parameters that we can measure at any given time in a halo catalog that will fully parameterize these things without taking into consideration the full history of halos themselves and their stochastic nature. So before I end off, I just want to put two cautionary notes. The first of which I think I might be the only one who actually cares about, which is essentially taking lambda CDM as a given. Rainer laughs because he says, yes, I agree with that statement. And the idea behind this is the following. So this is a particular exercise where there are 4 different gravity models that are shown here. So it's general relativity or lambda CDM in black, and 3 variants of something called F of R gravity, which essentially boosts the strength of clustering and enhances the halo mass function at very high mass scales. And each of these models have been tuned to essentially replicate the same galaxy catalog, the same number density, the same projected clustering, okay, as in observations, but you yield very different galaxy halo occupation distributions, okay? And this is essentially because the halo mass functions themselves are quite different. So where you actually put the galaxies changes. So there is a little bit of degeneracy between exactly what is the parameterization you use, the cosmological parameters, and the nature of gravity that you care about. Okay, the second cautionary note, and this is really done in spirit of the fact that I was supposed to replace Frank van den Bosch today, I would say that there is some pinch of salt required when we talk about how much faith we actually put into our simulations and what we infer from them. And really, I think a good example of this is some recent work that has been done which looks at the abundance of satellite galaxies in the innermost regions of Milky Way-like halos. So there's this particular work which says that if you have a disk galaxy in the center, they're prone to destroying a large number of subhalos at the center. And if one assumes the sort of standard sort of ways of populating galaxies and halos and reionization and so on, you would find that there are far too few galaxies in these models than there are actual observed galaxies in the real universe. So this is a sort of converse of the missing satellites problem. This is an overabundance problem. And so this is sort of visualized quite neatly in this figure here, which looks at the number of satellites as a function of distance. So the purple region is, say, the standard law for reionization quenching, as they call it here. The black histogram is the observed galaxy counts. And they say that you need to start populating much lower mass halos to actually be able to match up with the observations in the central parts of the halo because of the sheer amount of depletion of subhalos you get from the disk. Okay, and what that does is that it actually changes your galaxy halo occupation. So for the standard quenching, for the standard model, I suppose, you would find that essentially nothing below a circular velocity of about 15 kilometers per second is populated. Whereas if this were to be true, you would say that you would actually need to fill up every halo that is as small as 7 kilometers per second. Okay? So as an offshoot of another project that I've been working on, we've essentially been looking into radial distributions again, and just ignore the colored curves for the time being. So again, what I'm showing is the number of satellites as a function of distance. And on the left-hand side is essentially the number of galaxies that are identified with actual dark matter halos associated with them. So the simulation has identified dark matter halos, it's looking at what the galaxies are, and then seeing what are the final locations of these things. However, we know that all simulations and all halo finders have trouble when it comes to detecting substructures. Okay, so specifically there is a resolution limit below which simulations are unable to track subhalos, and especially when you get close to the center of a dark matter halo, when you're trying to identify an overdensity against a high density background, your halo finder always has trouble actually detecting these objects. So what we actually do is detect these things called orphan galaxies, which are essentially things that have actually formed in a dark matter halo previously, but their halos have gone below the disruption limit or the resolution limit of your simulation. But the galaxies are still tracked by knowing where they were before they just went under the hood, and then actually tracking the dynamics using some dynamic filtration calculations. And essentially what you find is that you get an almost order of magnitude boost in the abundance of populations of galaxies that you would get if you didn't actually track what these orphan populations are. Now, I should say that there is no disk disruption included in this, but what I want to stress is that disk disruption correction will be applied to essentially the figure on the right as opposed to the figure on the left. So if you're reducing everything by a factor of 5, we're only reducing things from 100 to about 20 rather than from 10 to 2 or whatever. And just one second. And essentially what that means is that you can come to very, very different physical interpretations for where and how far down the mass function is actually fill halos with galaxies based on simple numerical vagaries. Anyway, I will leave you with this as my summary.
I'm going to be that guy and just be super critical of your last point there. Though I completely agree in principle. But I think it seems a little unfair to say, but you often give you like a factor of I don't know how many more galaxies, and then you should apply this correction to that. But I think the galaxies, the subhalos that have been numerically disrupted, I think they would also be more likely to actually have been disrupted in the real world. That's probably because they will have come closer to the center of the halo or disk or whatever it is, right? So I think you can't treat those two things as two totally independent numbers. Now I completely agree with you that you have to take care of it, and it's probably
I guess I think the reading of the literal numbers of the plot I think is maybe a little too optimistic in this diagram. But I think the point I want to make is that where or how severe your corrections need to be, I think has to be done with a little more caution. I think that is as much as I argue.
Okay, another clarification question before we change speakers. Otherwise, we have some more time for more general questions at the end, that we can address, by both speakers. Okay, then let's change speakers.
Question and a comment.
I missed my chance.
Fully justified at the end.
Okay, thank you to the organizers for the invitation to give this talk, and thanks to Sownak for stepping in at the last minute due to cancellation. So what I'll be talking about is this paper here. It's on the archive and it should be shortly available in the journal. So if you're interested in anything I've talked about here, please take a look at this paper. Here is an HST image of dark matter.
Dark indeed.
Dark matter is not directly observable. When we point our telescope to the sky like HST, what we see instead is images like this. Tens of thousands of galaxies, which in our current cosmological model we believe traces out the large-scale dark matter distribution. And the real question is, how can we connect these objects to the dark matter halos within which they reside? And I think Sownak did a good job of giving sort of the theoretical approach, but one thing I think should have been taken away from that talk is we're sorely needing empirical approaches based on observations to test some of these theoretical approaches that Sownak was describing, and that's what the subject of this talk will be. The key step to doing this is identifying an observable proxy that can link galaxies to their dark matter halos. And we've been working on that for the last few years, and we've identified the stellar velocity dispersion, which can be directly measured using spectroscopy as such a proxy for quiescent galaxies. On the left, I'm showing a figure from analysis of the illustrious simulations. And what's being shown here is quiescent galaxies at Z of 0. This is 10,000 galaxies. This is the dark matter halo velocity dispersion versus the stellar velocity dispersion of the objects in illustrious. And the blue line is the one-to-one correlation. So in the simulations, what we see is that the stellar velocity dispersion is very nearly directly proportional to the dark matter halo velocity dispersion. We then went, motivated by some of these types of results, we went and looked in the observations where we have a survey of 5,000 galaxies for which we have stellar velocity dispersions. We sort those objects into 3 bins, so about 1,500 galaxies each, and look at the weak lensing signal around those objects and infer the velocity dispersion of the dark matter halo from weak lensing, and that's what's being shown here. So what's being shown here is the velocity dispersion for the 3 bins, measured from the stellar velocity dispersion, versus the velocity dispersion of the dark matter halo inferred from lensing. So this is purely observational, this is purely theoretical, and both studies are coming to the same conclusion, which is that the stellar velocity dispersion is directly proportional to the dark matter halo velocity dispersion. And then what that means is it's well known that dark matter halos are in virial equilibrium, so the stellar velocity dispersion is very tightly correlated with the dark matter halo mass. And we use this property in conjunction with observations to study the coevolution of galaxies in dark matter halos. So here's a beautiful image from the hectomap survey, which has been conducted here at the CFA, and the authors are listed there. And what you see is galaxies, slice of the universe, galaxies over the last 4 or 5 billion years in the universe. And what we're trying to do is understand how did these galaxies, which we see 4 or 5 billion years ago, evolve into these galaxies that we see today. And so we're essentially trying to connect the populations observed at higher redshifts, or what people normally call intermediate redshifts, to a low redshift universe. And the data sets that we're using is, for the local sample, we're using the Sloan Digital Sky Survey. So this is a survey that covers 10,000 square degrees of the sky. It's 90% complete to the magnitude limit. And it has good signal-to-noise spectroscopy of about 1 million objects. And by good signal-to-noise, I mean we can measure velocity, dispersions, emission lines, all the properties we're interested in. And for the intermediate redshift sample, we're using the SHELL survey, which is covering 4 square degrees of the sky. It's 15 times deeper than Sloan, but it has a comparable completeness. And it's a magnitude-limited survey. And we have spectra of about 13,000 galaxies out to Z of 0.7. And so the question is, in a statistical sense, how did the objects we see in this survey evolve into the objects that we see in this survey? The types of objects I'm going to be talking about today are massive quiescent objects, galaxies. Here's an example of one. These tend to be spheroidal. Their stellar kinematics are dominated by random motions. They are usually satellite central galaxies. Almost all of the objects, a huge, large fraction of our objects we're talking about central galaxies. And the fact that the stellar kinematics are dominated by random motions allows us to interpret the velocity dispersion as a virial quantity. So in this plot that Sownak had showed, we're talking about galaxies that sort of live above the mean. So in halos of 10 to the 12 to 10 to the 13 solar masses. The quantities we measure are the stellar masses using the standard techniques of mass to light ratio inference from population synthesis modeling. We do it consistently for both samples. We measure the half-light radius for these galaxies, circularized aperture, equivalent half-light radii. And for spectroscopy, we measure a couple quantities, but the first thing I want to say is when we do spectroscopy, both samples are conducted using fiber spectroscopy. So you center your fiber on the object. So the spectrum of a particular galaxy is representative of the central stellar population. We're not talking about global properties coming out of the spectrum. We're talking about the properties of the central stellar population. And the properties of interest are the velocity dispersion. So here is an example of 2 spectra of 2 separate galaxies, and the velocity dispersion is measured using from the width of the absorption lines in these spectra. So you have absorption in the stars of galaxies, and these stars are moving around, and the more rapidly they move around in the centers of the galaxy, the broader their absorption lines. And so it's a directly measured quantity. Here you see on top a galaxy that has a large velocity dispersion as compared to this one, which has a smaller one, and you can see it directly by the width of the absorption line. So that's how we measure the velocity dispersion. It's directly measured from the spectrum. And again, this is, as I showed earlier, is a property that directly links galaxies to their dark matter halos, because this velocity dispersion that we measure is the velocity dispersion essentially of the dark matter halo. Okay, and then the other quantity we use is the D4000 index. What it is it's measured again from the spectrum. It's a ratio of the flux in this band redward of 4,000 angstroms to the flux in the band blueward of 4,000 angstroms. And this index is very sensitive to the age of the stellar population. So young stellar galaxies dominated by young stellar populations have very flat spectra, and so their D4000 indices are very close to 1, slightly more. And as the stellar population ages, these absorption lines become more dominant, and the D4000 index increases. And so one of the ways we use it is to select the quiescent galaxies. So in this plot, what I'm showing is for 2 models, these are from stellar population synthesis, the D4000 index. So in red, this is the D4000 index of a galaxy that has constant star formation its whole lifetime. So initially, the D4000 index increases, but it sort of flattens out around 1.2. And that's where star-forming galaxies typically peak, D4000 indices around 1.2. In black, I'm showing a model in which you have constant star formation for 1 given year, and then star formation rate shuts off. So star formation shuts down. You see the D4000 index rapidly increases because these the massive stars are dying off. The absorption lines from intermediate and low mass stars become more prominent. D4000 increases. And we say that anything that has a D4000 index greater than 1.5 is a quiescent galaxy. And we check whether this is reasonable definition against other indicators, and it's as robust as anything out there, and it has advantages that we can directly measure from the spectrum. It's insensitive to reddening. You don't need K corrections, things like that. So, in the end, our samples with these measured quantities are from the Sloan, we have 100,000 galaxies, which are selected to be unbiased in stellar mass in order to derive unbiased relations for the local population. Selection is a very subtle issue in these samples. I'm not going to go into details today, but if you work with redshift surveys, you really have to be careful how you select these objects. And so we have 100,000 galaxies from Sloan, and we have out to Z/.2, and then we have 4,000 galaxies from the Shell survey from 0.2 to 0.6. So again, the question is, how do these objects in a statistical sense evolve into these objects? The primary observational constraints are shown in this plot, so I'll try to walk through them carefully, and if you have any questions, please ask. So what's being shown here on the left two panels is the Sloan data. This is 100,000 galaxies, but I'm showing the relations, I'm just showing the medians. So on the top, I'm showing the size versus stellar mass relation sorted in bins of D4000. So the blue curves are galaxies that have small D4000s, the red curves are galaxies that have large D4000s. And so what this plot is telling you is that at a fixed stellar mass, galaxies that are hosting old stellar populations tend to be more compact. Conversely, here's the plot for velocity dispersion versus stellar mass. Galaxies with old stellar populations tend to have higher velocity dispersions at a fixed stellar mass. And this can be understood as a consequence of virial equilibrium. Galaxies with old stellar populations are compact, so the stars are moving more rapidly. So that's for the local universe. This is what the properties of the galaxy population are as a function of stellar mass in D4000. Now, on the right two panels, I am showing the same properties, but now stepping out in redshift. So the black curves in both of these are the Sloan data, but no longer sorted by D4000. So it's just a median relation from Sloan. And then the different colored curves are the Shell sample stepping out in redshift. So what you see is that at a fixed stellar mass, as we look out further and further in time, the average size of quiescent galaxies is getting smaller and smaller. And this is well known. Conversely, the velocity dispersions of these galaxies is staying constant. And the question is, how can you reconcile these directly observed properties with the properties at higher redshift with the properties of the galaxies in the local universe? So the first thing you could say is, okay, what if the galaxies that become quiescent at early redshifts just sit there and passively evolve, right? What does that scenario, is it consistent with the data? So we could test that scenario. So as a preliminary step, the first thing I just want to show is that I'm going to fit these data points here as a function of D4000 and stellar mass. So here's the D4000 of the data. So these data points are the same as these data points. And the point is just that you're going to see in the future curves these straight lines. And you should just think that that is the properties of the local population sorted by D4000 as a function of stellar mass. And the other key step to linking galaxies across cosmic time is to use the D4000 as an age indicator. And so an example would be, let's say you want to ask, how does the average wealth of a person grow with time? So you take a survey of 20-year-olds in the year 2000, and you want to ask, okay, how did their wealth grow? Well, in the year 2010, you don't want to take a survey of 20-year-olds again, you want to take a survey of 30-year-olds, because there's been 10 years that have passed. Similarly, we have measured D4000 indices, and we want to trace galaxies as they evolve in time, because the D4000 index monotonically increases. So if you have a galaxy, let's say, at Z/.4 with a D4000 index of 1.5, this model tells us that by the time it evolves 4 billion years later to Z/0, its D4000 index will be roughly 1.85. Similarly, if the galaxy had a D4000 index of 1.7 at Z/.4, by the time it gets 4 billion years later to Z/0, it's almost 2. So we're connecting galaxies using their D4000 as an age indicator.
Wait, sorry. That only works if there's no new star formation or mergers.
That's correct. Well, mergers maybe not. That's a little subtle point. Maybe we can come back to this. It depends on the nature of the merger. But if there's star formation in the center, this is the key though. The fiber spectroscopy is sensitive to the central population, so it's not going to pick up any star formation on the outskirts. of the galaxies. But it's indeed true if you have rejuvenation of star formation at the center, which there's no evidence for suggesting that actually happens in galaxies, but if that were to happen, that would affect this.
And that only works for fixed metallicity.
Yeah, but we actually tried models with various metallicities. It makes no difference in our interpretation or any of the results I'm plotting or I'm discussing. Okay, so the passive evolution scenario. So in this scenario, galaxies shut down their star formation, and then they just sit there. And the only thing then that happens is that their stellar population ages with time. So the D4000 index increases. So we have our 4,000 galaxies in the Sloan sample. We know their redshift, and we know their D4000 index because we measure those. And we say, okay, let's artificially evolve the D4000 index to the Sloan population redshift, and then compare. And nothing else changes. So on this plot, the straight lines are, again, the Sloan population sorted by D4000. So all the colors for the data points and the lines are D4000, indicate the D4000 index. And so what you do is we evolved our 4,000 galaxies to the redshift of Sloan. So the D4000 index has been evolved. And then we just bin by D4000 in stellar mass. So each of these bins represents 100 galaxies. And we have to do that because outliers and things like that, and it makes for a lot easier comparison. And then we just ask, how do the Shell's galaxies look as compared to the Sloan population? So in size, for example, we see that there are no galaxies in Sloan as small as the galaxies we see at even intermediate redshifts. All the galaxies from Shells, these data points, are below the Sloan relation. Similarly, if you look at velocity dispersion versus the mass, these points, the velocity dispersions are too low. These red points should lie on these red lines if they just passively evolved into Sloan. And so what this already tells us immediately is there must be some sort of growth that's happening for these galaxies in between the time we observe them at z at 0.2 to 0.6 and today. So let's build a model that attempts to quantify that growth. That model is quite simple. It has 3 parameters. The first parameter controls how the stellar mass changes with time. And it's a function of D4000 and redshift. If you're interested, we could talk about what that actual function is, but it's a simple parameter, functional form. And the free parameter is this epsilon, which is sort of an efficiency of growth. Then the size of these galaxies changes just as a power law dependence on the change in stellar mass. And the velocity dispersion similarly changes as a power law dependence with beta as the power law index as a function, power law dependence on stellar mass. And so you have a model that has 3 free parameters. And what we're doing now is forward fitting this data to constrain these parameters. So this is what it looks like under the passive evolution scenario. Only thing that changes is the D4000 index. Now what happens when we apply our model? The sizes, the masses, the sizes, and the velocity dispersions all change. And what we're doing, the way we fit the model is we're minimizing these residuals in a chi-squared sense, right? So we're asking how can we shift the Shell's population into the Sloan population? And we do it in a chi-squared sense. We find the best fit. These are the model parameters. The main point is that the way we parameterize these, specifically these alpha and beta, these power law dependencies, allows us to compare directly to simulations. And so here's an example of a simulation from Phil Hopkins where he's looked at various growth scenarios for the galaxy population, and these particular parameters are consistent with minor merger-driven growth. So the Shell's population, intermediate redshift population galaxy, intermediate redshift galaxy, quiescent galaxy population is growing via minor merger. So the picture you should have in your mind is you have your galaxy living inside your halo with your stars at the center, and it's slowly growing by accreting discrete objects that are smaller than itself, so it increases both its stars, but it also increases its dark matter halo mass at the same time. So from the model for those 4,000 Shell's galaxies, we have this model. It tells us how the stellar mass changes. So this is a change in the stellar mass for those 4,000 galaxies that we observe. And because we've parameterized, the way the model is parameterized, this also more or less tells us how the size and velocity dispersion changes. For example, beta, which is about 0.4, you just multiply that by 0.4, that gives us the change in velocity dispersion. And the key step now is in the beginning of the talk, I said the velocity dispersion is a direct proxy of the dark matter halo mass, and that therefore we can get the because we have the velocity dispersion, we can get the dark matter halo mass, and we have the change in the velocity dispersion down, so we can track the change in the stellar dark matter halo mass purely empirically. And this is an important point I need to make. In the work I've been talking about, nowhere does theory come into this. We use the simulations to verify that the stellar velocity dispersion is directly proportional to dark matter halo velocity dispersion. But it only verifies. So these results are essentially independent of the theory and therefore provide a very strong test on the theory. So the first thing we look at is what is the dark matter growth rate for these galaxies. So this is the dark matter growth rate versus the dark matter halo mass. For the shell's population, this is all from the velocity dispersion and the change in the velocity dispersion. The black line is the median relation for the shell's population. The dashed and dotted curves give you the contours which contain 50 and 90% of the galaxies. And the gray band is just propagation of the parameter, our model uncertainties. So that's purely based on observations. And then the hashed region, the blue hashed region, is from an n-body simulation. This is the dark matter accretion rate from Fukui 2010, but it doesn't matter which simulation you take, they all give you very similar results. And the point is, at the massive end, they're identical. And even at the low mass end, there are small differences, but these could easily be understood as a consequence of our selection. We select quiescent galaxies, whereas in a simulation with an n-body simulation, there's no baryons. There are no galaxies, there's just dark matter halos, so you can't do those types of selections. In any case, at the end of the day, this is a very, I think, encouraging plot that the technique we're using is robust, and that, for the most part, the theory and the observations are consistent. We could take it a step further because our model gives us both the change in stellar mass and the change in dark matter halo mass. So let's look at the ratio of those two, right? Because objects are being accreted in the minor merger-driven scenario, and we're gaining both stellar mass and dark matter halo mass. What is the ratio of the stellar mass to dark matter halo mass, or the change in the stellar mass to dark matter halo mass? This black histogram is that ratio for 4,000 objects, and the red curve is just a Gaussian fit to that. And the point is, what this represents is the ratio of objects, the stellar to dark matter halo ratio of objects being accreted onto galaxies. And now we can ask, how does this compare to real galaxies in the universe, or ones we infer to be real from simulations? So here's the stellar to dark matter halo ratio versus stellar mass. Here are two stellar mass halo mass relations. And here's where that distribution translated, the 1 and 2 sigma of that distribution translated onto this plot. And so the point is, the ratios of objects being accreted are exactly the ratios consistent with real galaxies in the universe. This isn't way down here somewhere or way up there somewhere. It's right where the galaxies live. And so what this is saying is that here, the picture that it's painting is these galaxies up here are growing by eating these galaxies down here. Another way to look at this is in the stellar mass halo mass plane. So now this is stellar mass versus halo mass. Same relation as I showed previously. And now the arrow is the direction that galaxies move by the model that we've constructed. And the gray bands are the 95% confidence limits on that. And so what this is saying is the model we constructed, this minor merger-driven growth model that we actually empirically constrained from observations, is saying that galaxies move along the stellar mass-halo mass relation above the knee. And so in the absence of star formation, which may be due to AGN, this relation is actually set by hierarchical galaxy formation. It's set by minor merging. That's what sets the scaling of this relation, not AGN feedback, because AGN feedback doesn't grow galaxies. And so the takeaway from this is galaxies at intermediate redshifts, quiescent galaxies, are growing via minor mergers, and there are means that are now being developed, specifically the stellar velocity dispersion is a means to connect galaxies to the dark matter halos to study these processes. Thank you very much.
Clarification questions first?
Yeah. So,
yes, Margaret?
Jabran, how could you, what other observations could you bring to bear on this, so the minor, to look at the minor merger, I mean, with all the imaging surveys and so on, presumably?
Yeah, that's a good question. I mean, something we've discussed too, and others have actually looked into as well. I think one is the imaging surveys give you this, you see the satellites of these objects. You may not have spectroscopy for them, but you can't see them. So someone like Drew Newman, for example, has showed that in imaging, you can find the faint companions and ask, are there enough of them, and are the ratios of their masses consistent with this type of picture? And that's something we would like to do. That's just one example. I think lensing also holds a great deal of promise for studying these types of relations.
Yeah, so clarification question. When you talk about the velocity dispersions, which correspond very well between the mass and the between dark halo and stellar mass, stellar part, you can easily go from stellar velocity dispersion to the mass within the radius because you know the radius. But for the dark matter halo, you don't know the radius. So what makes you think that this is correct to go from velocity dispersions to halo masses?
Yeah, so there's some scatter in the, so if you look at just the dark matter halo and you ask the relation between stellar velocity dispersion and dark matter halo velocity dispersion and dark matter halo, they're scattered in that relation due to things like sizes, concentrations. That's always going to be there. You're never going to be able to get above that. But that scatter is not that large. And the point is that what is happening most likely is that these objects are isothermal spheres essentially, and the stellar velocity dispersion you measure is the velocity dispersion of the halo, and so that scatter, which is due to these other parameters, is there, and you have to live with it. I mean, I think a bigger source of scatter is actually anisotropy, and that's something you're never going to overcome.
Let's have Sownak stand up, and we can have a few minutes of discussion. We don't have that much time, so yeah.
So in this picture, this probably you can compare also to simulations and see if this is seen. I mean, usually people talk about AGN feedback, but
well, I would say
why don't you see that in simulations?
You may, but I would say one thing that you have to be careful about is AGN feedback is put into the simulations as a mechanism. It's not something that comes out of the simulations, and therefore you cannot use the simulations to test these types of questions. That's the point I was making before. You need observational empirical approaches. Otherwise, you're just running in circles.
Okay, no, I totally agree with that.
Yeah.
Did
I
you
mean,
have a comment on that? Looks
Exactly.
like you're the expert. Okay.
Exactly.
I mean the accretion process is part of the prediction of the simulation, right?
I'm sorry?
The accretion. No? Because of the AGN feedback? The accretion of halos.
Accretion of
The
halos.
accretion of halos.
The creation?
No,
The accretion of halos.
Yes, accretion of halos.
yeah, it's part of the prediction of the simulations.
I mean, you can do
say
that with n-body simulations without any hydro at all, right?
Right.
So you don't need the simulation.
Yeah, I meant the n-body. Yeah,
Sure. And so we were comparing to simulations, and in terms of accretion rates, they're consistent, especially at the massive end, right? I mean, that was what this plot showed, right? I mean, even down here, they're only off by a factor of 2 at most, and that's pretty good when you're talking about orders of magnitude over which these accretion rates could potentially
This
be.
actually confused me because you were saying you were selecting quiescent galaxies, and then you find that your accretion rates are higher than in the simulation. It should be the other way around, no?
Well, it depends. I mean, I talked to Andy Burkett about this. So at the massive end, there's no issue probably because you only have quiescent objects no matter what. So at the low mass end, the question becomes probably accretion is a environmentally dependent process in the simulations, presumably. Certainly in the real universe, it has to be, right? And so what it might be is that you're choosing objects that live preferentially in overdense environments, because quiescent galaxies do, and so they tend to have higher accretion rates.
No, sorry, that's a misunderstanding. You actually have lower accretion rates in crowded environments, and this is very counterintuitive. But even though you might think there's just more stuff to accrete, actually your tidal forces are larger. And so, let me get this right, so at fixed halo mass in a dense environment, you have a lower accretion rate. It's a bit weird.
But what kind of density are you talking about?
I mean, I
It
can't
does
really
make a
know.
difference whether it's a group or a cluster, because in a cluster of galaxies you have relative velocities of 1,000 kilometers per second, and a group is 300. So groups are, you have merging instability, right? Clusters, you have sort of the impact approximation.
So if you're talking about in a cluster, right, then I would say it's already been accreted, right? So like I think what people mean when, like by the statements that I was making, they mean more like large scale over density, right? So even say around your halo by like a few megaparsec or something.
But this includes every environment.
And also clusters, most of their mass formation is happening at late times, right? I mean, 50% of the mass in the cluster is from 0.5 to today. So
Depends how you count it, but yeah.
Yeah. So I think, I don't want to think too hard about this because I think the difference is small, and it could be due to systematics in the modeling, and also there's systematics in the n-body simulations, as you know better than anyone, or as well as anyone, that those exist and are problematic as well. So I mean, I think at the level of the systematics in both of these different approaches, this is, I would call it remarkable.
Yeah, I didn't mean to.
I don't think you did, but I think that's the kind of, the big picture. I think that's where we're at now.
Don't baryonic outflows and stuff start to affect you at this mass scale, or is that just lower?
I mean, again, it depends how you count, but if you count mass into some sort of Fourier radius, not really.
And it's probably sensitive to the mechanism. Is it some impulsive AGN blowout versus, sort of more? And so I think it's become so sensitive to, it becomes dominated by systematics, I think.
Can I ask a question? I had a question about this actually. So does the mass definition with which you correlate the stellar velocity dispersion for the halo, is that the same as the mass definition that is used by Fourier and stuff when actually defining what the accretion rate is?
That's a good question. I don't know, actually. I don't know. I think it doesn't make a huge difference at the level of this type of comparison, but it may, I think it makes 0.1 dex level of difference. It's not going to be like...
I think it will make more of a difference on the shifting left and right on that axis as opposed to up and down.
So I just took their equations at face value, I have to say, and for us it's just a straight conversion of the velocity dispersion into a dark matter, stellar velocity dispersion to a dark matter, so the virial equilibrium. So in principle, I would have to look into that more closely.
One more question for Sownak?
Yes, both, I guess. Sorry.
And then we got to wrap up.
Coming back to the previous point of comparing to the simulations. So my understanding is there's some magnitude of AGN feedback that is required for the observations to agree with the simulations, and that's what usually people say, that okay, this is because of AGN feedback. And now what you're saying, you don't need any AGN feedback to explain, no?
I maybe Sownak could say comment on this, but the only point I would make is you may need AGN feedback to suppress the star formation, but AGN feedback doesn't grow objects. It just stops them from growing. So how are objects growing on that relation? And it's by this hierarchical formation process.
Yeah, I think it at some level ties in with what I recently mentioned, which is that when you get this relation out of Buttons matching, you just get that relation. You don't really attribute any physical process to it. How we then go into the modeling domain and then actually retrieve that relation is a possibly equal fate somehow, right? But then it may well be that the AGN feedback that we sort of model at the moment and the extent to which it is model and how strongly it works is perhaps limited by other numerical things that we're trying to overcome in the process. But I think it would be hard to say that this is definitely due to this thing and not due to that thing. I think it would be and Rafa was going to say quite disagrees with both.
Okay, we're gonna give them a hand and then we can talk about it over coffee. Is that okay? We were told that we had to end early because otherwise people would get mad at us.
Next time, there's let me know what time later.
Did you think about mass loss? From the galaxies, there is mass loss in quantum galaxies.
From, you mean the stellar mass?
Yeah, it's pretty small. But it can be 0.1. You can just run your the SSP model, the simulation model you run.
Yeah.
Just run it for mass loss.
No, it's true. But I looked at analytical models, and D4000 of 1.5 is already well. Yeah, so I think
so disappointing.
But the majority of
Like the old stellar mass.
But I guess one point I would make on that let me think about that. Is that the third time that I had convinced myself to like second order?
Ideally, it is second order. The question is, you know, is it makes you feel something? You know, if you want to discuss these differences, then at some point,
that's second order. That's the point I have to think
and
about.
the other thing is you know, my favorite thing is like adding and supplement galaxies to population. So again, a second maybe third order effect.
No, and I think that my ultimate hope is that we still incorporate them. The difference is you can't use the D4000 index as a age process for star formation.
Right,
It's so central to star formation history. And so you can't do this type of model. You need something different. And there's probably other approaches. But I think it'd be worth talking about. I think in principle what you want to do is put the whole picture together, right? Where you have down here star formation works on, then you have some magic.
You could also look at number densities and see. But I mean, you have the data and everything like
and that was something very interesting in, which was
because you're sort of on the screen within your halo.
And then you just but if you know you get progressively more complicated, so you sort of slowly try to build this up.
It was extremely
cool. I'm glad you enjoyed it.
So the only point that is there is the same thing. You just stop stimulation and then you just get
This is bad.
And just introduce schematics. If it's not the same as for stellar component, because then your velocity dispersion will not be proportional. Like your mass will not be sigma square. Sigma square over r. So if for stellar and dark halo, there will be systematics and
but no, I mean, like, okay, let's just assume for a moment someone doesn't
feel like it's slow.
Well, I think it's right?
Maybe, I mean, the point of this though, right? Like,
the difference is
the step is that you show the velocity. So you cross the direct box with the dark matter.
Yeah,
Then the question becomes, how much scatter is there in those dark matter is actually velocity? There's no reason to dark matter halo mass.
No. It's not a question of scatter. Even if you assume that there's no scatter, basically all the dark matter halos have the same shape for human mass. Dark matter halo mass. There's a difference between the shape of the total mass and the vector radius that counted to the error. Then you will end up with an error because
that would be the scatter, right? That would be the source of the scatter.
No, only the scatter. You do the bias. Every mass will be slightly off.
Maybe I'm not understanding.
I completely agree with that. Especially if there's no difficult way to see what it does and so on.
So here is the relationship.
There's just no way you can use anyone.
Right. I never used that.
It seems obvious. I went to Galaxy Halo conference in 2016 or whatever, right? No, this was the sort of the snowpack conference in Utah. All right. Anyway, so the point was,
the question is how you converge this mass. Because in order to convert sigma to the mass, you need a radius. If the radius, of course you have a given mass.
But look at this. Here's what I'm saying. Here's this is the scatter. That radius.
and I think he's right.
I'll be away next week. Wednesday, I think, will become either this week or
I tried to raise this point Simon Muller and Simon White, and he was really from observation, we understand something about galaxies that we don't have.
No, I agree with you. The point I was making one advantage to all this is
But the escape principle helps you change
Is there a